So we are done with the confidence interval for population mean, and the next one is finding the confidence interval for population variance. Let us see what is the result for that. The theorem says that if you have a random sample coming from normal distribution and you have these 2 points A and B defined as this chi-square values for n-1 degrees of freedom, then 1 minus alpha 100% confidence interval for the population variance, that is sigma square, would be defined in this way. And if you have to calculate the interval for sigma, that is the standard deviation, then obviously we know that it will be just simply the square root of each of these terms. So let us see how do we get this result. So our third theorem says that if you have a random sample coming from normal with mean mu and variance sigma square, then the confidence interval would be n-1 times s square over b, n-1 s square over a, and it will go up to n-1 s square over b. So this is what we have to prove. Now if you recall, whenever we are dealing with variance, so I have said repeatedly that chi-square distribution would come into picture. And why it would come? Because if we have n-1 times sigma s square over sigma square, it follows chi-square with n-1 degrees of freedom. So we are going to make use of this result also. So for this, we know that chi-square is somewhat like this. It is right skewed. It goes from 0 to infinity. So here you have some value here. This is your A and this is your B. So if you look at this shaded portion, this is basically alpha by 2, and this B is basically chi-square alpha by 2 at n-1 degrees of freedom. And this shaded portion to this side is again alpha by 2, because we are finding actually everywhere you see we are working on two-sided confidence intervals. Your alpha gets divided into 2, that is alpha by 2, and such that the total in between the area, this area would be 1 minus alpha, so that the total area below the curve is 1. So A in this side it would be chi-square 1 minus alpha by 2 at n-1. So in both the cases we are writing whatever is to the right, what area is to the right of that point. So in this case it is alpha by 2, and in this case it would be 1 minus of alpha by 2, because alpha by 2 is this shaded portion. If you look at the remaining side, it would be 1 minus alpha by 2. Now with this information, we will try to prove your result. It said that probability, so we are basically focusing on this area now. So probability that n-1 s square over sigma square lies between A to B is 1 minus alpha. So if you simplify this interval, what do you get? You have to find the interval for sigma square, so it would be A over n-1 s square is less than equal to 1 over sigma square. This is less than equal to B over n-1 times s square. So this gives us that sigma square lies between n-1 s square over A, which is less than n-1 times sample variance divided by B. So your interval basically is these two endpoints, right? n-1 s square over A. So this is easy to calculate also, because if you know A and B, sample size is given to you, sample variance is also known to you, and you know at what confidence level you have to calculate. So basically you know alpha by 2 also. You know the degrees of freedom, so you can calculate the chi-square value for that. From the table you can see, or if you're using any software, then you can easily get this value. So it is very simple to see. So let us see an example for this. So if you consider an example says that suppose a pharmaceutical company produces pills with an intended active ingredient concentration of 20 milligrams per tablet. A quality control analyst at the company is concerned about the variation in the actual active ingredient concentrations and want to estimate the population standard deviation of the concentration. To do this, the analyst randomly selects a sample of 15 pills from a production batch and measures their active ingredient concentrations. The sample yields a sample variance of 3.6. Use this random sample data to calculate a 95% confidence interval for sigma, that is your population standard deviation, of the active ingredient concentration in these pills. So you are given the sample size, that is n, and for sigma, what else do you need? You need the sample variance, that is also provided to you, and you have been given 95% confidence interval at n-1, that is 14 degrees of freedom. So you can simply see that from chi-square table, if you substitute these values at 14 degrees of freedom, so since alpha over 1 minus alpha is 0.95, okay, so alpha is 0.05, divided by that and subtract from 1, it will be 0.975. If you look at this value, it will be 5.629. Likewise, if you look at chi-square value at this alpha, then it would be 26.119. Now you can just substitute. So you see that here in the numerator you have n-1 into the sample variance that is given to us, and you divide it by b over here. It would be less than this quantity over here by a. So n-1 times s square over b less than equal to sigma square, and here it would be n-1 s square over a. And if you simplify this, you will get the confidence interval for variance, and likewise you can see that the 95% confidence interval for sigma would be 1.39 to 2.99. B, and here it would be A. Okay, 1 by sigma square is there. Okay, so please make a note of this. Now coming back to your lecture. So this was basically about confidence interval for population variance, and now if we look at confidence interval for population proportion, the result says that for large random samples, your 101 minus alpha % confidence interval for population proportion is p hat plus minus z alpha by 2 into the standard error, that is p hat into 1 minus p hat divided by n. Right, so if you can see that this is the point estimate that we already have, and we also know that when we are dealing with population proportion, because binomial distribution can be approximated using your normal, so in that case we can use this z alpha by 2 comes into picture. And if you can recall from the sampling distribution concept, we studied these things there, so we are basically utilizing those concepts now. So let us see how to prove this. So our last result for this week is confidence interval for population proportion. We know that p hat minus p over p into 1 minus p over n, this is basically following your standard normal distribution. This we already know. Now I can simply use this concept. It would fall between minus z alpha by 2 to p hat minus p divided by p into 1 minus p over n, which will be less than z alpha by 2, and this probability would be 1 minus alpha. So if you can further simplify this for p, what you will get is, if you just look at this interval over here, you can multiply this, right? Minus z alpha by 2 under root p 1 minus p over n is less than equal to p hat minus p, and this side it would be z alpha by 2 under root p into 1 minus p by n. So if I now solve for p, what I get is, it would be p hat minus z alpha by 2 under root p into 1 minus p over n, and this side it would be p hat plus z alpha by 2 under root p into 1 minus p by n. Now if you can see that we are finding the interval for p, but still this proportion is present on both the ends, right? In the square root, p is present. So what we do is that we simply replace this population proportion with its estimate over here, that is p hat, okay, and the result would follow. So the interval now becomes p hat plus minus z alpha by 2 into p hat 1 minus p hat divided by n. So this basically is your confidence interval for population proportion. So if you know the sample proportion here, you know the sample size, and you know the confidence level at which you have to calculate, then there is nothing. It's a very simple problem. So let us look at the example now. Now let us look at the example for this. Suppose a marketing agency conducts a survey to investigate the preference for eco-friendly packaging among consumers in a city. And out of 600 respondents, 420 express a preference for eco-friendly packaging. Using this sample proportion, the marketing agency wants to estimate with 95% confidence the parameter P, which is the proportion of all consumers in the city who prefer eco-friendly packaging. So based upon the data they have collected from 600 respondents, they want to talk about what is the proportion of all consumers in the city who prefer eco-friendly packaging. So you want to find out the confidence interval for that population proportion. Now what is given to you? You are given a sample size. You are also given the sample proportion because it is 420 by 600 and 95% confidence interval. So you know that n is 600 sample proportion and z alpha by 2, that would be 1.96. So here we can just simply substitute it. So 0.70 plus minus 1.96, that is z value, and then here you will have 0.70 into this divided by n. If you simplify this, what you get is that the interval is 0.663 to 0.737. So basically you can be confident, 95% confident, that between 66.3% to 73.7% of the population in the city would prefer eco-friendly packaging. So based upon the interval estimates, you can finally talk about, you can generalize that statement for the entire population, provided you have taken a sample which is a correct representation of the population. So you can say that based on the sample that you have taken, you are concluding this. Now, in addition to the estimation process or the goal of estimation, which confidence interval estimation concepts helps us in achieving, we can also use it to support your hypothesis testing decisions also, provided it is a two-tailed hypothesis testing. So we have studied that in the previous weeks. What it says is that if the hypothesized value falls within the interval, you fail to reject the null hypothesis. Okay. So it means that if you have found out a confidence interval and now you have a hypothesis testing claim also, two-tailed claim, and you see that if the null hypothesis for that, if you see that claim and based upon that, if it falls within the interval, you would say that you cannot reject it. So let us see an example for this to understand it in a better way. Suppose you are 95% confident that the average time it takes for a particular task falls between 12.5 minutes to 14.2 minutes. This is the interval that you have obtained. Now somebody wants to investigate further that the average time is indeed 13 minutes. So the two-tailed hypothesis could be that the null hypothesis is 13 versus the alternative is that mu is not 13. So it does not take 13 minutes. Right? It can be either less than or more than. Now if you see that since 13 over here falls within the 95% confidence interval, okay, because the interval is from 12.5 to 14.2. So 13, that is the hypothesized value, basically falls in that interval. So you cannot reject the null hypothesis in that case, and you would say that you failed to reject the null hypothesis at level 0.05. So this basically completes your week 11, and we have seen confidence interval estimation for single sample problems, and we have focused primarily on population mean, population variance and population proportion. So in the next and the last week, we are going to learn about 2 sample situations, and we will find out confidence interval in those cases. In addition, we are going to learn about the bootstrap method for finding the confidence interval. Thank you.